Today we will see discrete Fourier transform. For a discrete time sequence, we define two classes of Fourier transform. First one is DTFT, that is discrete time Fourier transform for a sequence having infinite duration, and the second one is only TFT, that is a discrete Fourier transform for a sequence having finite duration. So in DTFT it has a sequence with infinite duration, and in DFT it has a sequence with finite duration. In mathematics, the discrete time Fourier transform, that is DTFT, is a form of Fourier analysis which is applicable to a sequence of values. The DTFT is often used to analyze the samples of continuous function. The term discrete time refers to the transform operates on a discrete data, often samples whose interval has a units of time. The DTFT is a continuous function of frequency, but discrete samples of it can be readily calculated via discrete Fourier transform, and it is the most common method of modern Fourier analysis. Both transforms are invertible. The inverse DTFT is the original sample data sequence. The inverse DFT is a periodic summation of the original sequence. The fast Fourier transform, that is FFT, is an algorithm for computing one cycle of the DFT. So, the discrete time Fourier transform provided the frequency domain omega representation for absolutely summable sequence. The Z transform provided a generalized frequency domain Z representation of arbitrary sequence, and these transforms have two features in common. First, the transforms are defined for infinite length sequence, and the second one is they are the function of continuous variables, that is omega or Z. In other words, the discrete time Fourier transform and the Z transform are not numerically computable transforms. The discrete Fourier transform avoid two problems and is numerically computable transform that is suitable for computer implementation. Given a finite duration discrete time signal, a corresponding periodic discrete time signal can be generated which has a t, that is discrete Fourier transform, and it happens to be a discrete frequency spectrum. So the given a signal can be represented by a sequence of a number. A special characterization of the signal can be obtained, which can also be represented by sequence number. Consequently, the DFT is highly amenable to processing by computer and digital signal processor. DFT turns out to be sampled version of frequency spectrum of the origin finite duration non-periodic signal, and therefore it is very important tool for DSP, that is for digital signal processing. It was demonstrated that the direct evaluation of DFT entails a considerable amount of redundancy, and through an method that has come to be known as the fast Fourier transform, it was shown that a huge amount of computation can be eliminated without degrading the precision of the DFT in any way. The FFT approach renders a highly amenable tool for computation, also a very effective one, and for this reason DFT has found a widespread application over the years. So for a length of n sequence, that is x of n, is defined for value of n is in between 0 to capital N minus 1, where only n samples of its DFT are required, and it is obtained by uniformly sampling of x of e raised to j omega on the omega axis between omega having value in between 0 to 2 pi. So from the definition of the DFT, we can write x of k equal to x of e raised to jw, and value of k is in between 0 to n minus 1, where x of k is also length of n sequence in the frequency domain. The sequence x of k is called as discrete Fourier transform of the sequence x of n. So using this notation, the DFT is usually expressed by this given equation. Now the inverse discrete Fourier transform can be given by using this equation, that is xn equal to 1 by n summation value of k ranges from 0 to n minus 1 x of k omega n raised to minus kn. To verify this equation, we have to multiply both the sides of the equation by omega and sum the results from n equal to 0 to n minus 1. Next is sampling frequency. The DTFT of x of n is defined as by this equation, where omega is a continuous variable. There are an infinite number of possible values of omega from 0 to 2 pi or from minus pi to pi. Thus, x of each omega can be computed only at finite set of frequencies. Next is properties of DFT. Since the DFT pair is equal to DFS pair, their properties will be identical if we take care of the values of x of n and x of k when the indices are outside the interval. So the first property is linearity. There are a number of properties. First property is linearity. Suppose x1 of n, x1 of k, and x2 of n, x2 of k. These two are the DFT pairs with the same duration of n. Then we will have this following equation, that is ax1n plus bx2n, ax1k plus bx2k. Now if x1n and x2n are two different lengths, then we can properly append zeros to the shorter sequence to make them with the same duration. The next property is shift of sequence. If xn is equal to x of k, then it is given by the following equation, that is x of n minus 1 mod of n. Note that here, in order to make sure that the resultant time index is within the interval, that is 0 and n minus 1, then we need to shift and it is defined by this equation, where r is the integer and value of it is given as below. So this diagram is for the shift of sequence. Next property is duality. For that, here the equation is given and this one is the condition. If x of n equal to x of k, then equation will be like this. Now the next condition is symmetry. For that also there is one equation which we have to remember as it is. The next is circular convolution. Consider x1 of a, x1 of k and x2 of n and x2 of k, these two DFT pairs with the same duration of n. Then we will have this following equation, where this symbol is a circular convolution operator. So circular convolution means what? It is defined for the periodic sequence, whereas convolution is defined for a periodic sequence. The circular convolution of two n-point periodic sequence xn and yn is the n-point sequence m equal to xn to yn, and it is defined by this following equation. The circular convolution is also known as cyclic convolution, and it is a special case of periodic convolution, which is a convolution of two periodic functions that have the same period. Periodic convolution arises So periodic convolution arises in the context of discrete time Fourier transform. In particular, the DTFT of the product of two discrete sequences is the periodic convolution of the DTFT's individual sequence, and each DTFT is a periodic summation of continuous Fourier transform function. Although the DTFTs are usually continuous function of frequency, the concept of periodic and circular convolution are also directly applicable to the discrete sequence of the data. So, in that context, the circular convolution plays an important role in maximizing the efficiency of certain kind of common filtering operations. The linear convolution. The linear convolution expresses the result of passing an image signal f through 2D linear convolution system. So the commutativity of the convolution is easily seen by making a substitution of the variable in double sum. Also, the linear convolution takes two functions of an independent variable and it converts them using convolution sum formula in a linear system or a digital signal processing. Basically, it is a correlation of one function with the time revised version of the other function. So multiply and sum while shifting one function with respect to each other. This holds a continuous time where the convolution sum is an integral or the discrete time using vectors where the sum is sum. Sum is a sum. It also holds for functions defined from infinity to infinity or for functions with a finite length in time. So circular convolution is only defined for the finite length functions, continuous or discrete in time. In circular convolution, it is if the finite length functions repeat in time periodically because the input functions are now periodic, the convolved output is also periodic, so the convolved output is fully specified. So the linear convolution is a mathematical operation which is done to calculate the output of any linear time invariant system given its input and impulse response, while the circular convolution is essentially the same process as linear. Just like linear convolution, it involves the operation of folding a sequence, shifting, multiplying it with another sequence and summing results product. So, however, in circular convolution, the signals are all periodic. Thus, the shifting can be thought of as actually being a rotations, since the values keep repeating because of periodically, hence it is called as circular convolution. Linear convolution is applicable for both continuous and discrete time, while the circulation convolution is applicable for both continuous and discrete time. In linear convolution, both the sequence, that is input and impulse, it may or may not be equal sizes. That is why may or may not have the same number of samples. Thus, the output too may or may not have the same number of samples. In circular, both the sequences must be of the equal sizes. So, they must have the same number of samples. Thus, the output of circular convolution has the same number of samples as the two inputs. Graphically, when we perform linear convolution, there is a linear shift taking place. While graphically, when we perform circular convolution, there is a circular shift taking place. In linear convolution, it is possible to find the response of a filter using linear convolution, while in circular, it is possible to find the response of filter using circular convolution after zero padding. Linear convolution may or may not result in periodic output signal, while the output of circular convolution is always periodic and its period is specified by the periods of one of its inputs. So these are the differences between linear convolution and circular convolution. So convolution is one of the most important concepts and it is used to determine the output of the system which produces for a given signal. and it can be shown that a linear time invariant system is completely characterized by impulse response. The shifting property of the discrete time impulse function tells us that the input signal to a system can be represented as sum of the scale and shifted unit impulse. So it will be reasonable to compute of the output signal as the sum of scale and shifted until impulse response. That is exactly what operation of convolution accomplishes. So the convolution can be used to determine the linear time invariant system's output from the knowledge of input and the impulse response. We can also say that convolution is a mathematical way of combining two signals to form a third signal. So it is the single most important technique in DSP. Using the strategy of impulse decomposition, systems are described by a signal called impulse response. So convolution is important because it relates the three signals of the interest: the input signal, the output signal, and the impulse response. So convolution provides a mathematical framework for DSP. So convolution is a formal mathematical operation like multiplication, addition, and integration. Addition takes two numbers and produces a third number, while convolution takes two signals and produces a third signal. It is also used in mathematics of many fields such as probability and statistics. In linear system, convolution is used to describe the relationship between the three signals of interest: the input signal, the impulse response, and the output signal. Thank you.